Hello students, welcome to the third lecture of units and dimensions. Today I will discuss about inertial mass and gravitational mass. So first you may distinguish or you must know what is inertial mass and what is gravitational mass. So first is inertial mass. When we assign mass to a body by comparing the acceleration produced in it by a force acting on it to the acceleration produced in a standard mass of 1 kilogram by the same force, then this mass is the inertial mass of the body. I will consider a given force produces acceleration a1 in a body of unknown mass small m1 and a0 in the standard body of mass m0 of 1 kilogram. Then we find that a0 upon a1 is equal to m1 upon m0. From here we can write m1 is equal to m0 a0 upon a1. Next we discuss about gravitational mass. We can use Newton's law of gravitation to assign mass to a body. We measure the force capital F1 due to Earth's gravitational field on a body of unknown mass small m1 and the force F0 on a standard body of mass small m0. Then we have F1 upon F0 is equal to m1 upon m0. From here we can write m1 is equal to m0 F1 upon F0. We measure both the masses one by one. So first we will discuss about the measurement of inertial mass. Inertial mass is measured by a balance which is known as inertial balance. This balance consists of a wooden block, this is wooden block, and a pan is fitted from this block with the help of two metal strips, and this wooden block is mounted on a table. When this pan is displaced by a small amount in horizontal direction, then this metal strip starts vibrating. The square of the time period of vibration of metal strip is directly proportional to the mass small m of the pan and the object kept on this pan. So T square is directly proportional to small m. If the time period of oscillations of two objects of masses m1 and m2 including the mass of the pan are T1 and T2, in this case we may write T1 square upon T2 square is equal to m1 upon m2. With the help of this relation we can obtain the inertial mass of any object kept on this pan. Next topic is measurement of gravitational mass. Gravitational mass of any object can be measured by a spring balance. As we know, if we suspend any mass from the one end of a spring suspended from a rigid support, the spring is increased in length. If a mass small m to be suspended from the lower end of a spring, on suspending this mass, if the increase in length of the spring is small x, then m is directly proportional to small x. Now if mass m1 increases the length of this spring by x1 and another mass small m2 increases the length of this spring by x2, then according to this relation we can write m1 upon m2 is equal to x1 upon x2. If m2 is standard known mass and increase in length x1 and x2 of the spring is measured, then mass small m1 can be calculated by this spring balance. Next is measurement of time. Each expressed time is a time interval measured with respect to a standard interval. Any event which occurs after a fixed interval of time can be used for the measurement of time. For example, the spinning motion of Earth around its axis. We have certain more examples. One is electric pendulum. Oscillator uses an alternating current of frequency 50 Hz. Due to this current, a motor is rotated to measure the time interval. Another example is quartz crystal clock. Quartz crystal has a piezoelectric property. What is piezoelectric property? Let us consider a quartz crystal. If we apply a variable pressure on the two opposite faces of a quartz crystal, then an electromotive force is developed on the remaining two opposite faces of the crystal having same frequency. This electromotive force can be used to measure any time interval, or you may say the oscillations produced are used to measure a time interval. Next, we use atomic clock. The period of oscillations of atoms are used to measure time interval in these clocks. Also, decay of elementary particles can be used to measure time intervals. We know that there are many elementary particles which are unstable in nature and their half-life lies between 10 to power minus 16 second to 10 to power minus 24 second. We can use this interval for the measurement of time. The careful observations of these decay processes can be used for the measurement of very small time intervals. Our next topic is significant figures. Any measured value contains certain reliable digits and one unreliable means uncertain digit. They together are known as significant figures. I will make it clear with the help of this example. Suppose the weight of a man is 65.23 kg. The digits 6, 5 and 2 are reliable and certain, while the digit 3 is uncertain. Thus, the measured value has 4 significant figures, 3 reliable and 1 unreliable. Here you have to note two things. First, that the number of significant figures does not vary by varying the units selected for measurement. I will provide you one example here. 638.4 centimeter and 6.384 meter. Both are same thing. One is written in centimeter and other is written in meter. Both of them are having 4 significant figures. And second thing is that it is customary to write the decimal after the first digit. That is, if there is a digit written 638.4 centimeter, then in scientific notation we have to write it as 6.386 into 10 to the power 2 centimeter. Now next we will study the rules for counting significant figures. First is, all the non-zero digits are significant figures. In case there is a decimal point, its position does not matter. We will have an example here. 27.73 has 4 significant figures. Next is, all the zeros lying between two non-zero digits are significant, no matter of the location of decimal point. Here is an example. 20.3005 has 6 significant figures. Here is 0. Here also there are 2 zeros. Next is, when there is no decimal point, the zeros at the end, that is trailing zeros, are not significant. Here is an example. 142000 has 3 significant figures. The 3 trailing zeros are insignificant. Next is, zeros on the right of the decimal point and to the right of non-zero digit are significant. Example, 32.00 or 0.3200 has 4 significant figures. Here also 1, 2, 3, 4. Here 1, 2, 3, 4. Next is, if the number is less than 1, then the zeros on the right of the decimal point but to the left of the first non-zero digit are not significant. For example, 0.006709. Here these two zeros are insignificant. So this digit has 1, 2, 3, 4. 4 significant figures. The trailing zeros in number with a decimal point are significant. Example, 0.0760 has 3 significant figures because this zero is significant and this zero is insignificant. You have to note here one thing, that if the non-zero decimal number is obtained by measurement, then all the trailing zeros are significant. For example, if the mass of an object is measured to be 30 kilograms, then it has two significant figures because this value is obtained by measurement. So this zero will be significant.